Someone stole my nameplate, by the way, out in the hall on my door. So if you guys come across a Mr. Giordano room 2224 nameplate, let me know. And if it was you, let me know. Okay, so I'm going to stop you. That's your time limit. So I did want you guys to see a couple of multiple choice questions. The very first year I taught this course, or 2 years ago, in this chapter, didn't do a great job of looking ahead. And so I created this note outline and I found these 2 warm-up problems. And I was like, oh, these look good. And so the very first year I taught this class, as we were going over the warm-up, here's what I started to do. I'm going to show you guys this. I was like, well, last time we talked about we had to find f prime and f double prime and f triple prime, and we had to find all those derivatives. And I started going and I was like, oh, product rule again. And I was like, this is taking for freaking ever. Then we got to kind of like the next lesson and I started to understand this stuff more. I had no understanding the first time I taught this class. I was winging it. I still kind of am, but I'm just better at hiding it now. But I learned that the reason you guys have to memorize these 4 right here is because they're going to use these 4 and you're going to have to be able to do a lot of manipulations. And this is what I talked about at the end of last class, was they might say, write the first 3 non-zero terms of x squared times sine of x. Well, what that means is you list out sine of x, but then you multiply all those terms by x squared. It's like you're multiplying both sides of the equation by x squared. Well, what that does for this very first problem, I've since realized, is if they have x squared be, or f of x be x squared sine x, well then look up here. Sine of x is this, which we do need to have memorized. I would definitely have the first, as long as you have the first few memorized, you can keep going with the pattern. But that means that x squared sine of x is whatever you get when you multiply all these terms over here by x squared, which is super nice because this problem asks for the first 3 non-zero terms of f prime, the derivative of this thing that I just wrote. What's really nice about it is the very first term is x cubed and its derivative is 3x squared, and there's only one answer choice with the first term is 3x squared, which means you don't actually have to keep going. But this is how you use those manipulations to your advantage. And the more that you have these memorized, a lot easier these things turn out to be. Does that make sense? Instead of actually finding all those derivatives. It's not wrong. I remember getting to the right answer 2 years ago. And then it was the next class that I realized, and I pulled this back out and I go, wait, guys, that we did not need to do all that stuff. Okay. The second very common question that gets asked is the second one here. So this is a very common question where they give you some sort of polynomial, some sort of Taylor polynomial, and they ask about the derivative of that function. So in this case, they're asking what f double prime of 5 is. Very common question. So here's what we know based on last class. In front of x minus 5 squared, in front of that term, we should have f double prime of 5 over 2 factorial, right? It's f double prime of 5 times x minus 5 squared over 2 factorial. Like the derivative, the power, and the factorial all match up. They're all 2s. So f double prime of 5 over 2 factorial is what should be in front of the parentheses there. And I know what's in front of the parentheses there, right? So this is the thing that should be in front of the parentheses. And I know the thing in front of the parentheses is 1 over 25, which means these 2 things have to be equal to each other. The thing that should be in front based on the formula needs to be equal to the thing that is in front of that term. And then I can manipulate that to figure out what f double prime of 5 is. Just multiply both sides by 2, and you get 2/25. Very, very common question that they ask about that. I see that one show up with Taylor polynomials all the time on AP reviews. Questions on those 2?
Hey, Mr. G.
Yeah. Don't you dare say it.
It's doing it again.
No, it's not. You're just, you are lying to me every time. I feel like it's a prank.
I'm sorry.
No, you're not. You're not sorry. You're not sorry. You were more than happy to turn your mic on and let me know that. Like you were giddy. You just couldn't wait. So could you guys not see what I was talking about?
No, we could see most of it. It was just like a weird bar towards the top.
Okay. Next time, screenshot and send it to me what it looks like. We'll see if you're telling the truth.
Lauren can vouch for me.
Yeah, but that doesn't mean anything. You guys could be in
You
cahoots.
say you don't trust Lauren? Wow.
I didn't see you're putting words in my mouth. That's like media spinning stuff. It was taken out of context. All right, you guys ready for the lesson today? I need you guys to be ready for the lesson. Are you going to Rose?
No, I didn't even apply there. I just remember to
Oh, I got in. Are you going there?
Yeah.
Yeah. No one else going there? I thought there was a few people that were planning on going there. You're going? I thought there was a few. Any of you guys planning on going to Rose? Yeah, there's some people in AB. Okay, so today's lesson. When I first started teaching this class, there were two lessons that like I went through the course and there were two lessons that kind of terrified me to have to teach. One of them was the area of polar graphs. Because at the time, I didn't know like how much I needed to know about polars. I didn't know if I was given a polar function, if I actually had to know what all those graphs looked like, and that terrified me. Then finding the limits of integration, I wasn't very good at, and I was like, if I'm not good at this, how in the world am I going to teach it? I don't know if I taught it well or not. But the other lesson that terrified me was this lesson today. When I first learned it, I was like, oh my God, this is terrible. But then I started looking at like AP style questions about this topic. They're not that bad. Once I started, and that's what I picked out today. I picked out kind of 5 or 6 like types of problems you guys are going to come across. They're not that bad. The hard part is this. So, you know, when we did alternating series and we were able to calculate the maximum error, like whatever the next term was, that's how far off like the thing could converge to. We looked at the next term. That's what we're doing today. We're actually able, if we use a Taylor polynomial, say we use a 3rd degree Taylor polynomial to estimate what a function actually is, which is the whole reason these things are a thing. I can actually use what's called the Lagrange error bound to figure out how far off that approximation actually is from the actual function value. So there are 2 types of error bounds you guys are going to have to be able to find in this class. The alternating series error, that's the easier one because that's just the absolute value of whatever the next term is. That one's pretty easy. This one is not so easy. So I'm going to show it to you. You don't need to write this just yet. We'll get there. But I'm going to show it to you. This is basically the thing that you guys are going to have to memorize today. Okay? This right here is kind of a formula that you guys have to memorize. All right? If you want to write it down now, go ahead and I'll kind of talk through it. I am going to start this lesson by showing like a 5-minute YouTube video of a guy doing an example with this, and then we'll kind of dive in. So just write this down for the time being. And then I'll talk more. I don't like talking when you guys are writing. Then you don't listen. I learned a lot of times in college, I would just not even take notes. My professors would like talk and go so fast that I just put my pen down and I just sat back and just tried to listen to what they were saying. Like taking the notes sometimes didn't help me. Doesn't that look fun? How many different letters we got in there? 1, 2, 3, 4, 5, 6 different letters we're working with in this formula. Kind of fun. My wife is off this block. I asked if she wanted to come in and learn this lesson. She did not. She was not interested in learning about the Lagrange error bound of Taylor polynomials. Can you believe it? Like, I'm recording this though, so maybe I'll just put it on YouTube and then send her the link. She'll watch it that way. She doesn't care. Okay, so there is a little typo on the notes. It's actually kind of a like important typo. It's where those arrows go on those notes. So the exact value is like the function value itself. But on your notes, that arrow is pointing to the polynomial, which is way wrong because that's the approximation value. It's just the formatting, like these things got shifted over to the right. So the exact value of a function is f of x. What we did last class was find the polynomial approximation, which is p sub n of x. Well, the exact value is equal to that approximation plus whatever the rest of it is, whatever the remainder is. This remainder is the thing that we are after today. We're trying to figure out how far off can that polynomial approximation be from the actual function. And that's what this is going on right here. This is what this is saying. You don't really need to worry so much about that gray box, to be honest. That remainder, that error, has to be at most the maximum of the absolute value of the n plus first derivative evaluated at z. I'm going to tell you what all this stuff means. I'm just kind of telling you how to read this. Times the absolute value of x minus c to the n plus first power over n plus 1 factorial. Essentially, if we're using a third degree polynomial to approximate, all the stuff to figure out the error, we have to look at the next term, the fourth. That's why it's n plus 1 in all that stuff. We're looking at the fourth degree, okay? Well, here's what these things all stand for, off to the side. C is where you are centered. Like the problem is either going to say you're centered around x equals 0, which means it's Maclaurin, or they're going to say you're centered around x equals 4 or whatever. Like they give you that value. So that's what the C value is. They're going to tell you what you are centered around, like what are you near to? They'll tell you that. X is the target value, which we'll talk about. Now, Z is kind of the toughest one. Like the tough part of this formula is really this part right here. This is the part that scared me. I was like, what in the world? And depending on the textbook you look at, and depending on the resource you look at, like they use different letters for these things. Like it always looks a little different depending on the resource you're looking at. I found this to be the easiest for me to understand. Z is a number between x and c. So let's say you're centered around 0 and you're talking about approximating f of like 0.3, right? So you're centered at 0 and your target is 0.3, like that's the number you're approximating. Well, that means that z has to be a number between 0 and 0.3, including 0 or 0.3. Like it typically is, you know, the c value or the x value. But our goal is to make this derivative as big as we possibly can. We are trying to look at the next derivative and make it as large as we possibly can within the interval that we're working with. Okay. When you guys come across a problem, and I think on the FRQ for homework tonight, there is one where you get to practice this. You can look at the rubric and see kind of how they score it. But I would encourage you, when they talk about the error for the Taylor polynomial, a lot of times they'll use the word Lagrange error, like they'll say that. I would write this right off the bat. I would have this formula memorized if it were me. Okay, I do at this point. I don't have a lot of like the inverse trig stuff. I don't have memorized. This is one that for some reason it sticks with me. Okay. So what I did, I was like, God, this is freaking hard. There's 2 people in the waiting room. Lauren and Vincent got kicked out. Lauren and Vincent, you guys got kicked out?
Yeah, I'm sorry.
What happened? Is it because I said I didn't believe you?
I don't know. My Zoom just crashed. Well, my whole iPad did.
Well, I'm glad you're back. You missed everything about the lesson.
Oh,
All of it. You have no chance now. Okay, so I was terrified to teach this. So what I did, and like I said, I'm going to show just a real quick video of a guy doing an actual application. I went through and found 5 multiple choice examples of these things in action. And like I said, as I was doing it, if you have the formula memorized and you know what needs to plug in where, these problems are not as impossible as what I was thinking they were going to be. So we'll practice using this formula. So I'm going to show you guys just a quick video. The guy is not exciting. Have you guys ever watched the organic chemistry tutor? He's good. He has a lot of good examples. He's very boring and dry. But for at least 5 minutes, he kind of explains this topic. And I think he does a pretty good job. So I'm going to start with this. The organic chemistry tutor, I think his name is. Yes. So I need to switch source, AirPlay, stop share. Got all this transitioning, stop share, share Chrome, enter the number 3013. Time me, go. Timing me? Okay. What's my time? 10 seconds? It's not bad. Oh no, the internet is crashing. That's not good. Why is it spinning? What's happening? This is terrible. Huh? I know. No. Come on. No. What did I just do? What is happening? Why is it so slow? Please play. Oh my gosh.
Anytime you type or text, Grammarly provides quality suggestions to help make your writing clear and engaging, and then come across the way you intend.
Okay, that's not the video.
Download today at Grammarly.com.
In this video,
Here we
we're
go.
going to talk about how to calculate the maximum error of an approximation
You don't need to
using
write.
Taylor's remainder theorem. So let's go ahead and begin. So what is the formula that we need to use? Here's the formula that you need. So the remainder is going to be the n plus 1 derivative evaluated at some number c times x minus c raised to the n plus 1 divided by n plus 1 factorial. So that's the formula we need to use. Now we need to determine what is x, what is c, what is n, and what is c. But let's start with n. What do you think n is equal to? What's the value of n? N is basically the last number you see here. N is 4. Now what about x and c? This number, we're trying to approximate the natural log of 1.1. That's your x value. Now the 0.1 that you see in every term, that's equal to x minus c. So if x is 1.1, c has to be 1, because 1.1 minus 1 is 0.1. So we have R4 of x, that's equal to f of n plus 1, so that's f of 5 of c, times x minus c, c is 1, n plus 1 is 5, and then over 5 factorial. Now what is c? Z is a number between x and c. So x, we said it's 1.1, c is 1. So z could be 1, it could be 1.1, it could be 1.05. Z is a number such that the fifth derivative will have a maximum value. So we need to find what the fifth derivative is. So let's start with the original function f of x, which is the natural log of x. The first derivative.
So what he's doing right now, he's trying to figure out what z value between 1 and 1.1, including 1 or 1.1, would make the fifth derivative of the natural log of x the biggest. And that was kind of the part that I was like, man, this is a lot of work. Well, you'll see on the multiple choice problems in the notes, they find creative ways to get you to find that maximum value. That's what we'll look at. Like they get very creative in their question asking. It's not very, a lot of times it's not very procedural. It's how do I use the info they give me in the problem to find that maximum value? That's what he's doing right now. He's trying to figure out how big can that fifth derivative possibly be.
The 1 over x. And then the second derivative, 1 over x is the same as x to the minus 1. So using the power rule, that's going to be negative 1 x to the minus 2. So we can rewrite that as negative 1 over x squared. And then if we take the third derivative, that's going to be 2x to the minus 3. And then if we take the fourth derivative, negative 6x to the negative 4. And then the fifth derivative is going to be 24x to the negative 5. So now that we have the fifth derivative, we have it as 24 over x to the fifth power. Is z going to be 1, 1.1, or some number in between? Which of those values will give us the maximum value for the fifth derivative? Notice that x is in the denominator of the fraction. And as you decrease the denominator of the fraction, the value of the entire fraction goes up. So we want the lowest x value. So 1 is lower than 1.1. So we're going to choose a z value of 1.
That makes sense what he's doing.
So f, the fifth derivative of 1, that's going to be 24 over 1 to the fifth power. So that equals 24. So that's R4 of 1.1, that's going to be, this is 24. And then plugging in 1.1 into x, that's going to be 1.1 minus 1, so simply 0.1 to the fifth power, and then divided by 5 factorial. Go ahead and type that in. So the remainder, the maximum value, is 2 times 10 to the negative 6. So that is the maximum error for this particular approximation.
So that's how far off. So that fourth degree Taylor polynomial. So you're trying to find natural log of 1.1, and you use that Taylor expansion, that fourth degree Taylor expansion. And if you enter all that in the calculator, you're going to get a value. What he just found is the maximum amount, your answer you got is off from what the natural log of 1.1 actually is. 0.00002. That makes sense? But the hard part in these problems is figuring out that maximum value of that derivative, that z value. Okay. Ready for the notes? Emery, you ready?
Absolutely.
Your shirt matches your mask.
Usually does.
Does it?
You just can't always see my shirt.
Oh,
I wear a sweatshirt.
I'm not very perceptive either. My wife will tell you that. So I don't notice many things. Okay. To the notes. Are you guys at home ready? You all need to say yes to proceed. What the crap? Nope, they're all there. Just messing with me.
Ready.
Oh, there we go. That's one. That's one.
We're ready.
All right, that's two.
We're ready.
All right, that's three.
We're ready.
We're ready.
Four.
We're ready.
All right,
We're
five,
ready.
six.
I said at the same time Vincent did, but we're ready.
7. Is that all we need? Is there just 7 of you? Yep, there is. All right, we can move on to to the notes. All right, we have 5 examples to do for the Lagrange air-bound for Taylor polynomials. Like I said, typically, because we have 2, we're going to have to keep in mind. There's 2 air-bounds we have to know. The air-bound for alternating series, which we've done. That's just the next term. And then the air-bound for Taylor polynomials. Most times they'll say Lagrange. I'm looking at the 5 examples I picked out. They say Lagrange here, Lagrange in the next one, Lagrange here on 6. I'm curious if they say it on all of them. They don't on this one, and they do on this one. So I guess we'll get into that. Okay, so number 4. We have a third order Taylor polynomial for f of x centered at 0 is 2x plus 2x cubed over 3 factorial. What is the Lagrange air-bound for f on the interval 0 to 2? So there's a lot going on, but we need to just kind of simplify the process. First thing, we learned a new formula, so I'm going to write that formula. We're dealing with a third order Taylor polynomial. So the way we notate that is r sub 3 of x. That's the remainder for the third degree Taylor polynomial. That has to be less than or equal to the maximum of the absolute value. Well, if we're dealing with a third degree Taylor polynomial, that means all the stuff in our formula is going to be like 4. That's what all the n plus 1 means. So it's going to be the 4th derivative evaluated at z, which we'll talk about. Now, it would be times the absolute value of x minus c to the 4th. But what is c in this problem? It's 0. We're centered at 0. It tells you that. Whatever you're centered at, that's your c value. So c is 0. That's your c value. So we don't have to write x minus c. We can just write absolute value of x to the 4th over 4 factorial. So this is what we're after. We're after that value on the right side, okay? We are trying to make all this stuff on the right side as big as we possibly can. That's our goal. We want all those values to be as big as we could possibly make them. So notice on this one, they don't actually give us a target x value, but they give us an interval. They give us an interval from 0 to 2 that we're dealing with. Well, if we're trying to make all this stuff as big as we possibly can, what x value are we going to be using? 2. We need to pick an x value on this interval, and we're trying to make this be as big as we can. So 2 is what we're going to be plugging in for x. We want to make that as big as possible. So on that interval, 2 will make that value as big as possible. So we're going to plug 2 in for x. The next thing we need to find is the biggest possible value of this. Well, this one kind of stinks because we actually do need to go through and find our 4th derivative. But since we're dealing with e's, it's not so bad. Just watch out for your signs. So we have f already. F prime is going to be, let's see, e to the x. And then the derivative of e to the negative x is e to the negative x times -1. So plus e to the negative x. F double prime, e to the x, and then that's going to be minus e to the negative x. F triple prime. And you just see that sign between them keeps flipping. Right there. So we're trying to figure out, okay, z, this number, this value right here, has to be a value between the c value and the x value, including the c value or the x value. It could be, typically it will be. Typically, you're going to be analyzing this derivative at either c or x, typically. Not all the time. They'll get creative and they'll find ways that maybe it's a number in between. But I'm trying to get this value to be as big as possible. Well, if I evaluate this at c, if I plug 0 in, let's see what happens if I plug 0 into this 4th derivative. I would get e to the 0 minus e to the 0 I get 0. That's not a very big fourth derivative value. Let's plug in 2. So then I would get e squared minus e to the negative second. Now, I don't know exactly what that value is, but I know it's bigger than 2. And it's very helpful if you look at all the answer choices, like you can actually see that number show up. That kind of tells you you're on the right track. So this is the maximum value of the fourth derivative. That's the maximum value. So I can basically fill in all this stuff now. The maximum value is going to be e squared minus e to the negative second divided by 4 factorial, and then times 2 to the 4th, so times 16. This is the farthest off we could possibly be. Now I just need to clean it up and match my answer choice. So 4 factorial is what? 24? 24. So 16 over 24 is 2/3. So we have 2 e squared minus e to the negative second over 3. Hey. I'm not going to stand up here and say, guys, these problems are really easy. They're not, but they are manageable. They're more manageable than when I was working through some of these problems. They would get pretty gross. Ready for the next one? I'm not going to do all of these. I'm going to have you guys try a few on your own, by the way. In fact, I probably wrote down which ones to have you do. I did 1, had them do 2, did 3, they do 4 and 5. You're going to try number 2. Get it up there, get it centered. Get it. No. Okay. There you go. Try this one. You gonna get it? I didn't know how much time you needed. That's right. Huh? Okay. You get B. B is the answer. So if you got B, nice job. You are Lagrange masters. If you did not get B, that's okay, because I'm here to direct you. So here's my work. This one was kind of nice because, like I said, they find creative ways. They gave the fourth derivative on this one. They don't want you guys having to spend a ton of time finding a bunch of derivatives. That's not what their intention of these problems are. So a lot of times they'll give you the derivative you need, or they'll give a table of values, or they'll give a graph of the derivative, and you need to just be able to pull the value from that for what you need. So my C value is 0 again. I'm centered around 0. My X value, again, is given on an interval. So I'm trying to pick the maximum X value. X is 2. It's over 4 factorial. And I need to get that fourth derivative to be as big as I possibly can between 0 and 2. And the number that will maximize this expression right here is 2. If I plug 2 in for X, I get E cubed, and that's as big as I could possibly make that fourth derivative on that interval. And then it's doing some math. What do you guys think of these? Fun? Are they fun? They fun? Okay. All right. 3. I'll do this one. And then you guys can do the last one. For your FYI. Okay. The third degree Taylor polynomial for f about x equals 5. So they're giving us C right there. That's where we're centered around. That's our C value. On the first two, C was 0. This one, C is 5. Is given by this third degree polynomial. The fourth derivative satisfies the inequality right here. The fourth derivative is less than or equal to 20 for all x in the interval from 5 to 7. Find the Lagrange error bound for the approximation to f of 5.5. So on the other two, they gave x as an interval, and we were trying to pick the biggest x value in that interval for x. Well, in this one, they're actually giving us our x value right here. They're giving us our target value. We're centered around 5, and we're dealing with f of 5.5. So 5.5 is our x value. So we have x, we have c. We just need to get that value to be the biggest. Well, I'm going to write our formula first and foremost. We're dealing with a third degree polynomial. So we're talking about the third degree remainder. Has to be less than or equal to the maximum of the absolute value of the fourth derivative evaluated at z over 4 factorial times the absolute value of x minus 5 to the fourth. The other ones, it was just x because c was 0. But it's always x minus c to the power. This one is super nice because they're basically telling you right here, the biggest that fourth degree can possibly be is 20. Like they're giving you that value. So this is what I mean. Sometimes they get creative. They just want to know if you know how to deal with the problem. Not so much find that maximum, but just how to deal with it. They're giving you this maximum. It's 20. And we know x is 5.5. So we just have to do some calculations. We have 20 over 4 factorial. And then it's 5.5 minus 5. So 1/2 to the fourth. I find students struggle with these sometimes more with the arithmetic than the actual problem, because you just got to figure out which of those fractions this value is. It's not hard. But especially when you're taking an AP test and you're like under a time constraint and you're like, oh no. Is that what you do? So this is 20 over, let's see, 20 over 24 times 1 over 16. Is that what that is? Did I do that right? 20 over 24, what's that? That 5/6. Is that right? Am I doing that right? 5/6. So 6 times 16 is 96. So D. All right. Questions on Lagrange? Okay. Whenever you guys try the next one.
Mr. G,
Yes. Yes, Holly.
It's happening again. I took pictures. I can send them.
Send them.
I will email them to you.
Please do. You probably
I'm not lying. I
photoshopped.
can't lie.
I bet
I'm
you
so, I'm so
photoshopped.
bad at it.
You photoshopped your pictures. I already know.
Uh-huh.
Yes, she would. They said you would do that. See?
Those liars.
Well, now I need to fix it.
All right, I've emailed it to you.
You guys have other teachers that do Zoom like this with the Elmo? No? I don't know if this issue that happens to me happens to other people. It does?
This kind of happens to this class.
It does? It's like a black bar?
I don't know about that. But yeah, he just forgets to switch.
Oh, that's different. That's his issue. Right?
Yeah. Or, well, sorry, as he claims, it just doesn't switch when he tells it to.
Well, I'm looking at what you're showing me, Holly. I don't see what you're talking about. A black bar?
No, it's not a black bar. Part of the screen like freezes as what it was before. So like it was stuck on the old problem. I took multiple pictures so you could see how it's still there.
Yeah, no, I see what you're saying. Yeah, you did a pretty good job of photoshopping, but you could have done
Yeah,
a little.
I'm a little rusty.
You
So,
could have done a little better to convince me, but it was pretty good.
yeah, so, you know, I'm a rookie Photoshop. So.
Yeah. One of my e-learning lessons last year, not lessons, but like sessions, I went to learn about Photoshop from, who was it? Who does the photography stuff? What's her name? Why, that's really bad. We taught together for like 14 years. She's right across the bridge on the right.
Miss Han.
It's Han, yeah. There's a lot of stuff that goes into that Photoshop. There's a lot. I left feeling overwhelmed. You can use a calculator on this one. I don't know if this is an actual calculator question. I would think so because the numbers get pretty hairy. So I used a calculator personally. I would think this is a calculator question. Otherwise, you have to do negative 80 divided by 4 factorial times 1.5 to the 4th power. Without a calculator. It's gorgeous out. Is that enough time on that one or no? People still clicking buttons. Keep going. I think the trick answer is E. You might get E. Did you get E? Yeah. I think that's the trick answer. You found how far off the actual value could be from the approximation. So which you need that value, but it says find the maximum value of f of 3 halves. Yeah. Yeah. So keep going. You do need that number. Crazy the it's like 1, 4, 3, 0, negative 80. What a wacky polynomial. So here is my work. This one's different because it doesn't say like find the error. It wants us to find how big that possible value could be. So we actually got to find two things. You have to find the fourth degree Taylor polynomial approximation for f of 1.5, which means you actually have to find the fourth degree Taylor polynomial from the info given in the table. That's why they're giving you all those values to actually write out the polynomial. That's what we did last class. So then I got to find that approximation at 3/2. This is why this has to be a calculator question. I can't fathom this being a non-calculator question because of time. So the approximation is negative 6.5. All right. If I did a fourth degree Taylor polynomial approximation of this function, I would get negative 6.5. I want to know how big could the actual value possibly be? Not what is the actual value, but how big could it possibly be? Well, that means I got to find how far off can this number be from the actual value. That's what this is over here. This is my error. So the biggest that fifth derivative can be is 160. They give you that right here in the setup, 160 over 5 factorial times 3/2 to the fifth. So the farthest off it could be is 10.125. So there's our approximation, and that's how far off it could possibly be. That's the biggest value we could have. Yeah.
Where'd you get the 6.5 again?
This negative 6.5?
Yeah.
So after I constructed the polynomial right here, then I plugged 1.5 in for all those x's, like with my calculator. That's why I said I can't see this being a non-calculator question. That would be terrible. Not impossible, but just not fun. The only reason I could see it being non-calc, I don't know if it was or not, is because all the answer choices are fractions. A lot of times if it's calculator, they'll have them be decimals, but I don't know. That makes sense? Got one more. Can we handle it? Am I losing you? Last one. If you get it right, you're the class champion. Anybody want to be the class champion? Who's the current class champion? It was Sam at the very beginning of the year. I remember that. But I don't remember after that. Let's play a little bet your booty again. We'll place your wager and get a new class champion. I like the sound of that. Steven's missing quite the lesson. I am recording it though. There's a tricky part on this problem, so be careful. They try to trick you, just FYI. This one is non-calculator, I think. But I don't care if you use calculator. You guys want to see it? Did you get A? It's not A. You get C? It's not C. Did you get B? It is B. The answer is B. I don't know what you would get if you got tricked. Is it if you did 96 instead of 60? So if you plugged 96 in for that maximum value, you got tricked. Okay, so that's kind of the tricky part of this problem. Everything else is kind of the same, but this is the first one where like you actually need to be careful about what your X and C values are. So first of all, your C value is 1 because you're centered around X equals 1. Your X value is 0.8. All right, so X is 0.8, C is 1. That means Z has to be a value between 0.8 and 1. Like you're looking for the maximum value of the third derivative evaluated at some number between 0.8 and 1, which means you can't use F triple prime of 2. That's not in like what you're allowed to use. So that's the trick part of selecting 96. Since it says the three derivatives are increasing, then that means the biggest possible derivative is going to be at 1. So this 60 value right here, the biggest the third derivative can be is when X is 1, and that's going to be 60 right there. So 0.08. Yay! Okay, so your homework tonight is an FRQ from, I don't know what year it's from. It's not in the far past, but it's just a question 6. I think it's a Taylor FRQ. I attached the rubric and I also linked a video explanation of a guy. This guy is like done every FRQ and does pretty decent explanations for like the past 15 years. So I put that on there too if the rubric doesn't make sense. So you guys at home, you are free to go. We'll meet Thursday and talk about power series. Peace out. Get out of here. Go. They're gone.